Hey folks, let's talk about Angular signals. So we have had like this Angular renaissance going on for a while now with all the cool stuff like standalone signals, control flow, defer, ES build, hydration, so many cool things, but today we are going to focus on signals and we are going to get pretty deep. But first, let me quickly introduce myself. My name is Thomas Trajan, a Google developer expert for Angular, and I build, teach, write, and speak with and about Angular. So if you are interested, check out angularexperts.io, which showcases all the services and products which we provide for Angular developers to make them awesome. Now, why Angular signals? Well, there is a lot of hype in the front end environment for a couple of years now, and like the main figure in that space being Ryan Carniato from the Solid.js, and also there have been like implementation of signals for the view in form of the refs. Then the Preact has signals and Quick with use signal. So what the signals promise for Angular is the introduction of simpler and more powerful way to manage state in our Angular applications. And of course, better developer experience in form of a simplified developer contract where signals just do what you expect them to do and should be easier to learn than to wrap your head around RxJs observables, at least for the people who are just starting with Angular, right? And then the very big one is that with signals, there is this promise from the Angular team that they will be able to tackle the performance of our Angular applications with the signal-based components and even provide a way to a zoneless future, with Zone.js being this library which basically triggers change detection in our Angular applications today, usually whenever there is some kind of event, be it like a user interaction or something asynchronous, right? So all those things sound really good, and that's why most of the folks got really excited about the signals, and all of these things are actually happening today, right? So you can already use signals in your applications today. So speaking about that, let's have a look quickly about on the timeline of Angular signals. So the RFC was released in April 2023. It was a huge RFC, right? Like the main document linking to four other documents, one of them being, basic signals and then the signal-based components, all the cool stuff, which then led to a initial release of subset of Angular Signal APIs in May 23 with the Angular 16, and those APIs being Signal, Computed, and Effect have been released in developer preview. And now recently in November, there have been another major release of Angular, being Angular 17, and Signal and Computed are already out of developer preview, being stable, but is the stable with the star because the effects are still being heavily iterated on to unlock the potential for that zoneless future and signal-based components. So now going into 2024, what we are looking or expecting from Angular team is to release stable effects, signal-based components, signal-based inputs and outputs, queries for view children, content children, and the support for zoneless Angular applications. Now, between the 16 and 17, there have been quite some changes in the internal implementations of the signals, effects, and the reactive graph, all these cool things. And the reason for that is that the Angular team basically iterates on how this is being done so that they can provide all these things which they promised in a way that is non-breaking and performant. And we hope that as we move towards the future, the amount of that playing with the internals will get smaller and smaller until we get fully released stable signals and performant zoneless Angular applications. Now, when speaking about the signals, from my perspective, it's kind of like this new piece of a puzzle. So many of you probably have seen this picture from the documentation of the RxJs, which I find is extremely useful. And back in the day when I first learned about the RxJs back in 2016, was extremely important piece of information which helped me to make order in the way I think about all these things, right? And this basically lists four primitives in the front end, and most of us are very well versed with using of functions, promises, and hopefully today also observables, right? And then the main difference being is like, is it a pull or a push based primitive? So if you have a function, you know that whenever you call a function, you have to call it, you have to pull the value outside of the function, and that function will give you single result or a single error, right? Now let's compare it to a promise. With the promises, we might trigger the logic which will kickstart the promise, but then it's the promise who will decide based on what happened when it's fulfilled or rejected. So again, like single value or single error. And then only then, when it's fulfilled or rejected, it will call and push the value to our handler, which we provided during the promise creation, right? So it's the promise who decides when we are going to get called. Compare that to the function where we decide. Now with the observables, it's a similar story like with the promise. It's the observable which is going to push values to our callback whenever they happened, but it will not be just a single value or an error, but it can very well be 0 all the way to, infinite, theoretically, values of 0 to n. So what about signals? Where do the signal belong on this chart, right? Because signals promise to simplify the state management in Angular applications. Well, as it turns out, signals are basically push-pull based reactive primitive, and on that level, they are kind of more complicated than the RxJs observables, which are purely push-based primitive. But as we will see very shortly, signals can hide all this complexity behind the scenes and basically deliver developer experience where they behave in a way that is intuitive, all the way to that you can say that signals just work. Right. So to recapitulate, Angular signals are eager push, lazy pull based reactive primitive for Angular, and soon we are going to explore more of what is hiding behind that statement when we go for like a deeper dive of how actually are signals implemented in Angular today. So, but as we said, Angular signals behave intuitively and just work, and that's that main promise that people using them will experience intuitive behavior because the developer contract is relatively simple. Now, in original version of this talk, I went through all the signals API, or how to create signal, how to read the value, how to update it. But I think at this point of time, most of the folks already seen like some basic information about the signals. So we are going to skip this and only focus on a couple of recent developments and important facts to take note of. So first of all, when updating signals value, we had 3 methods: set, which allows us to replace the current value; update, which allows us to update current value based on the previous value; and then we had the mutate. And the good thing is that the mutate API has been removed in Angular 17. So this in generally, personally, I consider it to be a good step in the right direction, because mutating your data breaks a lot of functionality in like basic Angular itself. So the most typical example being when you use the default change detection, if you mutate data which you are passing through inputs to some kind of component, the NgRx lifecycle hook will not be called, right? So in general, you always want to perform immutable updates, and that goes also for that update method, which in theory would allow you to mutate the current value of that signal which you receive, but we always should opt for immutable approach to performing updates in our state in Angular applications. Great. So now, like putting everything together from the perspective that signals just work, we have here like an example of an extremely simple Angular component which showcases all the 3 APIs. So we are creating now some signal, then we create derived data in the computer where we take the value of that signal, modulo 2 with reminder 0, that means it's even, and then we can use that computed signal in an effect, and that effect will rerun any times the value of that computed signal changes, and it will log that into the console. So now let's have a look at this following example. So this is example from the presentation, right? And it showcases that Angular signals just works, right? And also that very simple developer contract. So for example, with the effect, we only need to know that effect will run once initially, and then whenever any of the reference signals inside of its implementation change. So now it was true, right? And now as we increment, the effect runs, but because this is false, we are not going to log, right? And now if we increase to increment again to 2, it will rerun all again, and now it's even, so we also get that log. And if we reset, we set to 0, right? So everything works as expected. Also, as we are accessing the signal values in the template, we will see that they update as expected. And that's why we say signals work as expected. Now, cool. So yeah, Angular signals behave intuitively and work as expected, while hiding the complexity behind the scenes. Now, Angular signals are reactive, right? Well, yes, but it's a bit more complicated. So signals reactivity. Now let's imagine, or let's just say, if you never seen signals, then this example will be very interesting. And if you already seen and played with signals, then imagine you see them for the first time, right? So we have this code example where we define count as a signal 0, and then we access that value of the signal inside of the console to log the current value, and then we update the value of the signal by setting its value and even calling the update function, right? So what will be the log output and why? So of course, if you already seen signals maybe in Angular on in some other frameworks or libraries, you will probably say that of course it's 0 and only once. But why, right? Because if you see it for the first time, maybe it's not so obvious, because we learned that signals are reactive, right? That means they rerun the logic whenever they are changed. Well, as it turns out, maybe not every logic. And we are going to get the answer to why very soon. So now it's time for the actual deep dive, and we are going to go very deep. So based on the picture, it might be as deep that we will not be able to come back, but let's see what happens. So when working with signals, again, as we said, like, behave intuitively and do what they are supposed to do and just work. But as you can imagine, working in practice in large organizations, in large teams, and large applications, people tend to combine things in unpredictable way and unexpected ways. So everything just works until there is the behavior which you are experiencing in your application is strange, and you need to understand why. And for that, it would be very useful to develop a couple of mental models which will help you to basically navigate what is going on behind the scenes with signals in those rare cases when they don't do what you would expect. So and those mental models are: what is the reactive context and reactive graph? And in that reactive graph, who is the producer, who is the consumer, and what kind of consumer? So is it non-live, live, or transitive-live consumer? And also that single node of that reactive graph can be sometimes both producer and consumer, depending on like from which angle you look at it. And that's specifically important for the computed. And then what is the push and pull phase of the reactive graph and the reactive algorithm, which is also tied to that producer-consumer dynamic. When is it eager? When is it lazy? And as you can see, based on the colors, probably this corresponds a little bit to those phases of the reactive graph. And for the pull part of the reactive, or the reactive phase, what is the impact, how the equality of the values is calculated, and what is the value version. And this will have a big impact on that overall laziness. So, and those are also the things which have been changed over time between the version 16 and 17 and improved greatly. And here I would like to acknowledge that even though we are going deep, we still stay somewhat on a somewhat medium level. So if we went like completely to the bare bones source, there would be even more complexity and details in terms of like performance optimization. But I think this medium level of those mental models should be more than enough to be able to determine why something happened in your application. Great. So the reactivity, if we go back to our example and check that count, which is signal 0, and we know now that the log will be only called once and it will be 0, but now let's explore why. So as it turns out, reading signals pulls the current value, but only when we do it, so when we call that console, right? So it's lazy. And even though updating signal value tends to send an eager push notification that its value might have changed, so this kind of like this push phase of the reactive graph where we push the dirtiness, it's only the reactive live consumers who get notified about such a change. And the console log is actually not a reactive live consumer. And this is our answer, right? So if we re-implemented the browser console, if we overridden the implementation and implemented it as a reactive node, and especially like a live reactive consumer, which should be possible in practice, we could write such a console which would rerun as a response to a signal being changed. But of course, the console available in a browser out of the box doesn't have this behavior. Great. So this put it all together, but of course, now we are going to look at each of those mental models in isolation to slowly build it up. This was just as an example how it can help us determine what is going on and why. So our first step is talking about Angular signal reactive graph. And to understand the graph, we have to first speak about the reactive context. And basically with this example, we can see that whenever we are reading a signal value or a pulling value out of signal, inside of the computed implementation function called computation function, or in the effect implementation function, or even in Angular template, we are inside of a reactive context, right? So that means that somewhere behind the scenes, Angular needs to know, or especially Angular reactive graph needs to know that we are currently running the callback inside of the computed or inside of the effect or in the template. And that way it can create that connection inside of the reactive graph. So how it actually looks like in the source, if you open the GitHub repository of Angular and go to the reactive graph implementation, you would find that there is an actual global variable which stores the active consumer. So that means whenever we start executing this function, then this computed will be set as an active consumer. And then whenever we are accessing that value of the signal, it will create an edge inside of that reactive graph connecting the two of them together. So accessing signal value, pulling the value inside of the reactive context, for example, effect, creates a new edge in a reactive graph. An Angular reactive graph consists of producers who are pushing the dirtiness eagerly and consumers who pull the current value of a signal, but this pull is with a star because we will see later, once we start talking about the laziness, that this might not happen in under every circumstance. Right. So in terms of like building the reactive graph, there is also a little bit of nuance which has to do with what kind of consumer we are dealing at that moment. And let's start with the non-live consumer. And the typical example of non-live consumer is computed. So here we can see we have a signal 0, and then we want to calculate or like get the derived state with the computed if it's even. And then here I have a typo ng on init. Of course, we are going to pull value of that computed. So as we pull that value, that means this computation function runs. That means once we are accessing the signal inside of that computation function, there will be an edge created in the reactive graph connecting the two. And the pulling signal value in a non-live consumer will create just a unidirectional reference from non-live consumer to the producer. So the no dirtness or the push phase of the reactive graph will happen in this specific example. So if we try to visualize this, the reactive graph for computed or like a non-live consumer will look something like this. So there will be like a unidirectional reference from the computed to the counter, which is a signal, and then we can pull those values. Now, what about the live consumers? So the typical example is effect, but also Angular template. And here we can see we have a signal, and then we use it in a reactive context of that effect. And pulling signal in a live consumer will create a bidirectional reference, so the producer, the counter, will eagerly push the dirtiness whenever it changes to that effect, so that effect can schedule itself to rerun and then lazy pull that value out of the counter. So then the reactive graph will look something like this. As you can see, we have bidirectional edge between the two. Now the last example is a computed which became live because it was used in another live consumer like effect or a template, which makes it transitive live consumer. So again, signal computed for the derived state, and here inside of the effect we are calling that computed. So the computed will become live consumer, or specifically transitive live consumer, and again it will have a bidirectional reference. So the reactive graph will look something like this. And now whenever we update the counter signal, it will push the dirtiness that its signal, so that its signal value might have changed, and it will push it to the computed, and the computed will propagate it to the effect. And of course this represents like the simplest possible reactive graph, but you can imagine there being additional branches based on how those signals are used inside of another computed signals, effects, or template. So to summarize, not everything about Angular signals is reactive in both directions. So it's the push versus pull phase of the reactive algorithm, and only live and transitive live consumers are bidirectional. That means effect, template, and computed, as long as it's used transitively in either effect or template. So with learning all of this, now it should be possible to answer this quiz which I posted recently on Twitter. So we have a counter signal, right? And then we define the computed state, and here we do like a little bit of a no-no for debugging purposes, that we put console cold as a side effect inside of the computation function, so that we know whenever it runs, whenever it was executed. And here we use that signal to determine if it's even, right? So this is our setup, and now we are accessing the value of the counter, and this is just going to be ignored, but we are still doing this, right? And then we update the value of the counter by replacing it with the set, and then we update it with update, we increment it by 1, and after that we pull the value of that counter again. And the actual question is how many times the console log is going to be called. So now please think about it for a second, and I strongly believe that it should be like trivial after all this explanation, but the correct answer is 0, and the reason for that is that computed is a non-live consumer, and it needs to be pulled to like perform anything, right? And we are not even calling it once. So from that perspective, there won't be any edge created inside of the reactive graph, because for that to happen, we would have to access that counter signal at least once inside of this computation function, and this have not happened inside of this code snippet. Great. So reactive graph gotchas. So signals used in the reactive context, what does that actually mean? I would like to demonstrate it on this example when we have an effect, and here we have a condition which has a 50% chance of like being true, and then we are going to access a signal to log it out like as a side effect, right? So we learned that the effect will react to the changes in the signal, and it will schedule it run, and also it will run initially. But what if on the first run this condition evaluates to false, right? So then we had a 50% chance and it didn't happen, and because it didn't happen, we might be changing the value of that counter signal as much as we want. It won't have any impact on that effect because no edge in the reactive graph was ever created, and therefore the counter signal will never push the dirtiness to that effect, and that effect will never run again. So how to fix that would be to extract this effect or the accessing of the value of that signal on the line before that condition in some variable, and after that we can still have a logic including that randomness when we not always want to perform it, but only with the 50% chance, but we are guaranteed that this effect will be rescheduled whenever the value of that counter has changed, right? And this can be, I don't know, in some kind of game, or if you want to show some kind of pop-up on your website based on chance, or not to every visitor or something like that. So it might have a realistic use case. Great. Now, the flip side of that coin is that here we didn't want to miss any kind of signals we wanted to react to. Now, the flip side of that coin is that we do not want to react to changes of some signals, right? So consuming signals without updating the reactive graph. So let's say our effect depends to multiple things like counter and current user, and who know what other signals which are hiding in a call of this function. Now, we only want to this effect to run whenever the current user has changed, but not when the counter has changed or whatever other signals we might be accessing inside of this function. So in that case, we can wrap that call to signal with the Untracked, or even put the whole call of some other third-party external code, be it from our application or some libraries, in this Untracked callback, and the signals which are going to be accessed as a part of the execution of such a function won't be added as an edge in a reactive graph. Great. Now, a little bit on the separation of the push and pull phases of this reactive algorithm. So here we have a code example with a signal, and then in the constructor we are defining an effect which should react to that signal, of course. But then we also set the value of the counter, and then even after that we update it, right? And now the question is how many times this effect is going to run. And this is something which, the way I understand it, is basically very Angular specific from that signal's perspective. And to correctly answer this question, we need to understand that effect schedules itself on the microtask queue, and this code runs synchronously at like constructor time. So what does that mean? We define the signal, we define the effect, great. The signal starts as dirty, and it schedules its own run in the microtask queue. And then still synchronously we set the value to 1 and then update value to 1. So those signals definitely push the dirtiness through those through the reactive graph. But the thing is, because this effect didn't run yet, this signal was not yet added as a dependency inside of that reactive graph. So those are basically ignored, and even the dirtiness was not really pushed because there was no edge in the graph yet. So only after this effect actually runs, it will access the value of the counter for the first time, and only then the edge in that reactive graph between the counter signal as a producer and effect as a consumer will be created. This also means we are going to get the latest value of that counter signal when the effect ran for the first time. So that means it was 0, 1, and then 1 plus 1, so it's going to be 2. So as you can see, there are a couple of things in play, right? And we always have to think about the timing, and this is something which Angular does, I think, very thoughtfully, that it fully separates the push phase from the pull phase. So you will never really update the values in the signals in that single execution. Now let's get to something very interesting, which is laziness, polling, and the value versions. So first, let's have a look at an example, and that example is here. So we have a simple laziness. Let's rerun this again. And as we can see, we have a setup with the signal computed, which uses the signal again, is even, and then this is even is used inside of the effect. And now we know that like Angular schedules that first run of an effect in the microtask queue, and then it reruns. And for that effect to be able to basically know the actual value, it first has to run the computed, and only then effect runs. So far, so good. So now the question is, what is going to happen when we start incrementing value of that counter, right? So if we do increment by 1, we see that both the computed and the effect rerun for each increment. And the reason for that is that if we increment by 1, then the value of that computed also changes for every increment from true to false and back. This means also from the effect perspective, the value has changed. But what if we do +2? And now we can see it's only the computed which is rerunning, right? So not the effect. And now another example, if we call reset, then the computed ran once, but now if we keep clicking on reset and set value to 0, then nothing is going to happen, right? So let's explore this more visually with regards to reactive graph. So now we are going to talk about the interaction between push, pull, and pull in the reactive algorithm. So our first example was we had a count which was updated by 1, and then it sent a push notification to all its consumers, and it goes through the computed and effect. And because the computed is using the effect, it becomes the reactive transitive-live consumer, and effect is a live consumer, right? So the effect receives this push notification that some of the producer's value might have changed and schedules its new execution in the microtask queue. And what happens then? So let's have a look at this diagram. So the first thing which happens is that when the effect starts to run or like execute behind the scenes, it doesn't just run its own implementation immediately and pull the values through the reactive graph, but the first thing which it will do is to poll its producers. And polling means like it's the effect is asking its producer, which is the computed, is even, did your value in fact change? I received the dirtiness, but did you actually change? Right? And then the is even is like, well, as it turns out, I'm also dirty and I don't really know. So I also have to ask my own producers. So then the computed is even starts polling the counter signal, and the signals themselves, whenever they have been updated, they kind of know if their value has changed, because the value version will be updated by 1, as far as I understand. Right. So the is even is polling the counter signal, and the counter signal replies, well, yeah, in fact, I have changed. And then is even will run its own computation function, and during that run, inside of that callback, it is accessing the value of that counter signal. So during that run, it will pull the current value of that counter signal, right? And then it will use it. And then, because it was +1, so we went from 0 to 1, so we were even true, we will recompute that even is now false. So after that, the is even can answer back to the effect, well, yeah, in fact, my value has also changed. And then effect is like, well, that means I should rerun too. And then finally, that implementation function of the effect will run, and during it, it will again access the value of this is even, so it will pull the value outside of that and perform that side effect, and it will log out the value, right? So now we had this other example, if you remember, that we incremented the count by 2, not just 1, right? So again, we updated the signal value. The signal sends the eager push notification to all of its consumer, which propagates through the reactive graph synchronously that its value might have changed. So the effect again schedules its run on the microtask queue, and what happens now? So it's a similar story. Effect is like, okay, I received the dirtiness, so I need to ask my producers, did you change? And again, the computed receives that poll, and again, it doesn't know, so it also has to poll its own producers. So, and that's also like a point where we can illustrate that from the effect perspective, the computed is a producer, but from the computed perspective, the signal is the producer, and it's also a consumer of that signal, right? So the computed can be both producer in that direction and consumer in this direction. And again, because we updated signal, the signal kind of knows that I have changed, and then the answer to that poll is true. So then the is even will recompute, and during that recomputation, inside of this computation function, again, it will access the current value of the signal and use it to compute. So we went from 0 to 2, so is even stays true. So then is even replies to effect, well, in fact, I rerun now, but actually my value didn't change. So the effect will not rerun. And that's exactly what we've seen in that live demo. Now, the last example was we reset value of the count to 0 multiple times. So in this case, the way this is implemented currently is that the signals, they basically perform an equality check on their value, and if the value is the same, then there is no push of the dirtiness through the graph. So they don't even notify their consumers that their value might have changed. They know that. And as a side note, it is possible to override the equality function, and it will work great on the computed. But if you try to do it on a signal and return, like override it with a function which always returns false, we will get a warning in a console which says that even though you think is not the same, we know is the same, and therefore there will be no dirtiness pushed through the reactive graph, which I think is a very reasonable default. Right. So laziness summary. Laziness applies to the pull phase of the reactive algorithm, which means that the pull is optional because it only happens if the value of the producer did in fact change and the consumer actually needs to rerun, right? So the consumer polls the producers to see if their value or value version has changed. And here it's good to notice that values could be, in theory, large objects or arrays. So therefore, what Angular works behind the scenes with is just a kind of like a counter or a value version which increases monotonically for every change. So from my perspective, this is just like a simpler and cheaper way to get exactly the same outcome. And the computed can be both producer and consumer as we move through the reactive graph. Polling will rerun some producers, as we've seen with the computed, but it still can stop with them, right? It doesn't mean that everything will rerun under all circumstances. So the consumers don't run if the value version of the producer stays the same after the poll. So always be mindful of the fact that computed and effects are lazy, right? So it might not happen. They might not rerun. It depends, right? Did their value change? So they might not run on every interaction. So there is a bit of a nuance to that statement that effect or computed runs whenever signal changes. Well, yes, they do, but it has to be evaluated between each two nodes of a reactive graph. So changing one signal somewhere far away in a leaf node doesn't mean that all the nodes between that signal and some end effect or a template changed as well. And we have to be mindful of that fact. So now, similar but a bit more complex, to illustrate another point. So we have a situation with just a couple of more elements in that overall equation. So we have now two counters, A and B, and then they are consumed by their respective computed. So one is even, so that's kind of the same as before. Another one is consumed by is larger than 5. And what this means is that as we increment from 0 to 5, it will return 0, and then from there it will return 6, 7, 8, 9. So let's just quickly show it: 3, 4, 5, 6, 7, 8, right? So just to show like that the value stayed the same. So let's refresh this, and then both of those computed are consumed in yet another computed. Double if is even, so take this value and double it if this is even, else keep it the same. So here we get 0, then we get 6, and if this was even, then we will get 12, else it will stay 6. And this is then consumed all the way back in the effect, which just logs out the value of this signal. Right. So here we can see again, if I basically keep increasing this one, then this one changed and this one reruns, but the effect doesn't run, right? And here, if I keep increasing this again, the computed reruns, but nothing else because its value stays the same. So, and once we come to a higher number, and finally this next level, another step in the reactive graph, computed changes, only then we are going to get that computed and the effect. So to not spend too much time, let's just quickly have a look on how this looks like in the tree. And here it's also important to notice that we have two branches of the reactive graph, and if we are only performing update here, the push dirtiness will spread like this, and here nothing will happen in this branch of the reactive graph. So that's another thing to realize, that it goes only from producers to consumers, but if this branch is from the perspective of this computed are producers, the dirtiness will not spread. So when we update this counter, it will invalidate like the value, it will say it's dirty, and it will propagate it all the way to the effect, because this is a live consumer. So again, those are transitive-live, so everything was as expected. And now we are going to describe one example, and the counter A is 0, is even is therefore true, counter B is 0, larger than 5 is 0, then double if even is 0, and this ran as an initial run of an effect, and then we do counter B plus 1. So what's going to happen? The effect schedule its own run, and then it starts polling, and then it polls this first computed, and then the computed polls another computed, did you in fact change, and that other computed polls the counter, and again counter knows that it changed whenever there was a set or update. So as we recompute, so here it answers yes, I changed, so it's a true, so we recompute, and during that recomputation we pull the value, and we see we were 0, now we are 1, so this is still 0. So then this poll answers like, in fact, well, I did not change, and also it means that this computed revalidates its value and sets dirty to false. So from that perspective, if there have been other consumers which are scheduled at other time, if they would be accessing that larger than 5, it would not be even polling anymore, because it would not be dirty anymore, right? So you can revalidate, and then maybe some other consumers will not even trigger this anymore. And here is the similar situation. This was not dirty to start with, so it just replies, no, I'm good, and that's it. So the only thing which executed in this specific constellation of all things coming together was this computation function. And this didn't run, and the effect also didn't run. Right. So as you can see, it can get a bit more complex as our reactive graph is growing, but employing those mental models and having an understanding between the push and pull phase in the reactive graph, we can definitely make sense and deterministically be able to say what will run when and why, which can be very powerful when we need to debug real-life applications on our day-to-day job. So now a little bit about the Zone.js. So what is the current role of the Zone.js with regards to signals? And for that, I would like to use this very simple example with the signal, which we use in a template, and then we have a button where we increment that signal with update +1, right? So what happens when user clicks on the button today in Angular, and it's an on-push component? So the component template is also a live reactive consumer. So clicking on the button updates the signal value, and that signal will send the eager push notification that its value might have changed to all its consumers. So here the consumer being the template, and the template is then notified and marks itself as dirty and all its ancestors for traversal, which is a new thing, and more on that later. But actually none of that matters, because this is currently in standard Angular basically the most basic scenario, where when we click and we have an event, then the component and all its ancestors are marked dirty anyway as a standard on push behavior, right? So, and then of course Zone takes over, and what happens is we had a button, we clicked on it, and the Zone picked up that click event, and it schedules a new change detection application reference tick in the application root, in the root component. And because we clicked, all those components on the way to the application root have been marked as dirty, and therefore Angular will run change detection on every single one of them, all the way back to that component where it will re-execute its template binding, and during that time it will pull the current value of the signal, right? So this would work exactly the same for a basic property. So if what we did here was just counter as a basic 0 and then counter plus plus, it would behave exactly the same today, right? And this will change for better in the future. But we already mentioned this marking of all the ancestors for traversal, and this is a real thing, and we can show this with a slightly adjusted example where we don't have a button, we just have a counter, and then in the constructor we schedule the updating of that counter value in 5 seconds, right? And now it's kind of similar as before. After 5 seconds, the timeout will update the signal value, which will send the eager push notification, and the template as a live reactive consumer will receive it. And then the template will be notified and mark itself or the components dirty and all it ancestor for traversal. After that, Zone.js takes over again, where we had a set timeout, which is a API which is patched by the, or monkey patched by the Zone.js, so it knows about it. And again, it will trigger the change detection in application root, but now all those components which were marked for traversal will be skipped. So let's see this in action in a demo. So we have this very simple application where we have like a root, and then we have two branches of components, like a sibling branches. So one is with 3 children which are nested in each other, and another one is just a single child. And let's just start with, and all of them are on push. So let's start with something very simple, which is already today the way it is. So whenever I click on a basic increment, there is just some kind of property which gets updated. Or actually, no, it's a signal which gets updated. But because we clicked all those components all the way to the root where marked as dirty, so therefore, whenever we click, this all blinks because the template bindings have been rerun, and we also have these counters that the amount of change detections has increased, and then the value in that signal has increased. And in the previous example, we've shown that this works exactly the same if it would have been a basic property counter, not a signal. And as we can see, this is true, right? And then what onPush does is that it's just that single branch of the components all the way to the root, but not the sibling. So here, the other way around, is just this component, but not this branch of components. They were never marked as dirty. So now we've seen that if we use something like a timeout or an interval, it should behave differently, right? It should be just the component itself, which was marked as dirty, but all the ancestors should be marked for traversal. So let's try. So the first click, of course, it was a click. It marked everything as dirty, so the whole thing blinked once. But after that, whenever we update the signal on interval, what will happen is signal pushes the dirtiness notification to the template. Template marks itself as dirty, components for traversal, plus the Zone.js starts from the top. And as we can see, it's only this component where the template bindings are being reevaluated, which is pretty amazing. And of course, this is a bit of a contrived example, but let's just say we have some kind of global service, and then one part of UI updates the value in the signal inside of that service, and another part of UI is consuming that value from that service. And as you can see, here we have a click, so of course still today's Angular on push, dirty all the way to the root, so this has to of course be reevaluated. But inside of that other branch, Angular already knows that it's only this signal or only this component which consumes that signal that needs to be like rerun its template bindings, right? So as you can see, using signals even today before signal-based components and the zoneless Angular can lead to massive performance gains when we don't have to do the whole application or the whole subtrees, which with like non-trivial larger applications can have a lot of positive impact for the end users, right? Because the application will feel much more responsive. So this is something to be really excited about. This is something which we should definitely try in our code bases already today, especially if we are managing state with something like a behavior subjects. Their signals represent like a no-brainer upgrade for the overall performance and maintenance of such application. So now it's time to get back to reality. So We have explored a lot of mental models and how signals work behind the scenes. Again, it was not like completely the lowest level. There are other optimizations going on, but I think this is the level at which it will allow you to determine what happens in your application the best. But of course, feel free to check out the actual Angular source. It's a very interesting read, which will provide you with even deeper insights of what's going on when user clicks or the signal value is updated, right? Great. So now a couple of notes on how to use signals in practice today being December 2023. So that means before the release of the signal-based inputs and outputs, or the queries like view children or signal-based components. So this is all based on an experience from a real life project, which is basically component library, custom made component library for an enterprise organization. So imagine like an internal Angular material where we already employed signals in simplification of some of those components where it was a good fit. So, and one of those challenges which we encountered was how to do host bindings with signals, which is not so trivial. And as it turns out, Angular supports this host property in its add component decorator, which from what I heard was available since Angular 2. And this one allows us to write this kind of statements where we can basically write the standard class, Angular class binding, and then attach it to a specific signal. And one thing to notice is that this is actually a string, which seems a bit like a very fragile thing to do, but currently there is pretty good support for that in WebStorm or like IDEA, which will highlight and validate these statements, and you will be able to click through to that specific signal, right? Or it will say like if you made a typo. For other editors, I don't know, but obviously it is possible. So it's like only a question of time when the support lands for all of this. And who knows, maybe Angular team comes up even with like a better way. But already today it is possible to do a signal-based host binding like this. Only thing to remember is that this is basically an ESLint error from the standard subset of the Angular recommended rules. So you would need to disable that rule in your application. Another one is handling inputs without the signal-based inputs. And for that, there is a very nice idiom where we can basically alias input to that standard name which we had previously and use a setter with underscore. And like a benefit of this approach is that we do not have to have the signal with underscore. The underscore is only used for the setter. So then once the signal based inputs are available, all we need to do is to just delete this workaround code and rename signal to input, and everything just works. So, and we had quite some of those because we have a lot of inputs on our components. So we thought like, would it be cool to like automate this a little bit? And yes, it would. So I'm a big fan of using regular expressions. And there we came up with a statement which you can then copy. I will provide the link in the description. And if you use this regex in your editor in a search and replace dialog for that specific file and replace it with this, it will basically, yeah, it matches all those possibilities with, you know, the type or without the type, with infer type, with the default value, without the default value. And it will give you those workarounds with the underscore, with the alias, and then the only thing you need to do is to reshuffle it a little bit. And I personally like to put those at the end of the file with the to-do, so to just remove them once the signal-based inputs are available, and also just rename this from signal to input. And because this is like close to the top of the component implementation, then you already get a feel for how it's going to look like once the signal-based inputs have been released. So you also get a better feel for how much less verbose signals are compared to other solutions, right? And I mean, this is not nice, but it's hidden somewhere at the end and it's just temporary. So why not? You can start using signals like this already today. Now, for the view or content children, we added such a workaround, which is probably even dirtier, but it gets the job done, at least in our project. So basically we don't have, or we don't want to depend on the lifecycle hook of after in this case after content init, and we work around that fact by using timer 1. So we basically do it after 1 millisecond, and at that time the content children was already populated. Maybe 0 he would work here also. I haven't tried that, probably. Yeah. And the cool thing about this is that we can already use this to signal, which basically signalifies that stream and also unsubscribe when the component is destroyed, right? And then we switch map and we concat the initial value with all the changes. So this works as expected. And again, once we get the proper query, or it will be called like content children or whatever, we just delete these old content children and replace this workaround with the actual API provided by the Angular. Right, so then there will be a link to an actual demo. Let's skip that for now. Signals and RxJs, yes please. There is an interop API provided by the Angular team, Angular core RxJs interop, which allows us to go there and back with ease. Simple API just to method, to signal, to observable, which has to run in injector context, or we have to provide an injector. And I really like to showcase it on this very typical search or type ahead example where we always want to debounce and cancel the previous one, the most iconic example for the usefulness of RxJs, where without RxJs, this will lead to race conditions and inconsistent UI state, right? When you search for something, the responses from server are not guaranteed to arrive in exactly the same order as they were dispatched or emitted. So what do we do here? We have a signal, which is the query in the input. So as we type like what we are searching for, and we use template-driven form to set the value and update the value whenever the value in the input changes. And then we streamify this signal with the observable and use all this cool stuff from RxJs, where the RxJs brings actual value to the project. So we debounce, so we only want to trigger the request when we stopped typing, and then we only want to trigger request if there was still some like value in the input at the end, if we didn't just delete all the characters. And then we switch map that query into the basically service which performs the backend request. And again, this will cancel the ongoing request if there was another request which prevents those race conditions. And this is just the stream definition, cold stream definition. Nothing runs until we subscribe, right? And to subscribe, we switch back from the stream definition to like a signal. So this to signal will subscribe behind the scenes, and we also define the initial value of empty array. And then we just use that signal in a template, and here I'm missing the function call on that signal. So imagine here is this function call. And then as we type, it will behave exactly as you would expect and exactly as you would want. So there is still place for RxJs. Config options, please check the docs. So signals do not make RxJs obsolete. We can get the best of both worlds by playing to their strengths. And again, people tend to overuse RxJs over time in places where it wasn't really necessary. But there is this part of logic which really deals with asynchronous orchestration, where RxJS is in fact very useful, and we should keep using it in that place to deliver applications which are robust and don't leave user in inconsistent UI states, right? Or worse, that we do something bad in the backend because the updates were not in order. So there is definite place where RxJS delivers a lot of value to real-life applications. What about NgRx? NgRx 17 was also just released with a completely new signal store and related APIs. It also provides us with a way to switch to RxJS and back with Rx method, which is a natural fit for previously, NgRx effects, which perform this kind of stuff. It has a new functional API, which makes it extendable, which is an amazing feature because it allows us to basically wrap some of our repeated functionality, which was relatively verbose with the standard NgRx, and wrap it up as an NgRx signal store features, prepackage them, and then include them in those stores as one-liners. So I'm really looking forward to see what community builds with this over time, and what new best practices and patterns will be abstracted away and win in the competition of the ideas. So yeah, best of both worlds, we get strong structure, but it's still extendable and allows us to abstract away project-specific logic. And there is, from what I understand, no plan to deprecate standard NgRx store based on pure RxJs, so we can keep using that onwards to the future. Example how it looks like: signal store with state with computed, or with methods, and then the methods can perform also something asynchronous in a robust way with Rx method. And then there is this helper coming from the library, which allows you to basically update the state back in a store in a simple way. Cool. So a little bit about the future of signals. So what we are really looking forward to are inputs and outputs, view children, content children model, maybe for a two-way binding with signals, stable effect implementation, signal-based components, and the support for zoneless Angular applications. And from what I've seen, the latest update from Alex from Angular team, it may very well be that the plan has changed, and it seems to be the case that it will be first the zoneless support with on push, and only then the signal-based components. But from our perspective, who cares as long as it happens, and it should happen in 2024, maybe even in the minor release. So hopefully very soon. Great. So the journey continues, and as it looks like, Angular journey will be full of Angular signals and a lot of performance and simplified code in our code bases. So there are links to all those examples and to our blog, and again I will share this in a description so you can check it out. And of course, last but not least, if you are working with Angular in your organization, we are offering various consulting and contracting services to empower your teams, so please do not hesitate, get in touch. Also, check out our new blog at angularexperts.io/blog with a lot of cool articles and in-depth articles about the latest Angular features and best practices and real-life examples. Also signals, even though this is now a little bit outdated, especially because all those changes, right? So, but the general idea holds, and I hope I will find time to update it to reflect the latest and the greatest. With that being said, thank you for your attention. I hope you enjoyed this and learned something about the Angular signals and will use them in your code bases. Until next time, see you.